Hi everyone, this is your struggling CS student here, and today let's solve another LeetCode problem of the day. Let's take a look at today's problem, uh, 333.46. Okay, sorry, 3,346. Maximum frequency of an element after performing operations 1. So there might be a harder version of this problem, and it's already 1800 rated. Okay, so let's see. You're given an integer array nums and two integers k and num operations. Okay. You must perform an operation, num operations of times on nums, where in each operation you select an index I that was not selected in previous operations, and you add an integer in this range to nums of I. Return the maximum possible frequency of any element in nums after performing the operations. This is kind of reminding me of the coordinated problem that was like maybe like last week or a few days ago. Let me just check that real quick. I'm not gonna check the solution or whatever. It's just that I couldn't solve that problem either. Is it this one? This one? I think it's this one. Is it this one? Nope. Wait, is it this one? Nope, I don't think this is the one. I think it's this one. Or is it this one? Wait, this is a super crack problem, right? Yeah, that's the super crack problem. Nope. 3000 rated. The first time I've ever seen a 3000 rated question, by the way. Um, Let me see. Any? Is this the one? Ah, surely you know what? Mm, I saved it somewhere because I remember I couldn't solve it. I think this might be the one. Yeah, this is the one. 3397. When was this? When was last month? 3397. Okay, I don't really remember. 3397. Wait, wait a second. Okay, I'm not gonna look at the solution, but I sort of remembered the solution. Uh, but yeah, they also have like this kind of thingy. I remember not being able to solve this. Who knows? Maybe I submitted it like the solution after I seen it afterwards. I don't remember. Well, let's take a look at this problem. You're given an integer array, blah blah blah. Okay, so you must perform an operation this many amount of times, and in each operation we select an index that was not already selected, and we add the number in the range, and want to return the maximum possible frequency of any element after performing the operations. So let's take a look at an example. Input nums. Um, so you have two operations. And you can add -1 and +1 to any number in this range. The maximum frequency that you can obtain is 2. Adding 0, oh, you can add 0 to the number as well. Oh, because you must perform that number of operations. Well, from example 1, we can kind of see that sometimes we can do a no op because we can just add 0 to any number. Right, so in that case, what we really want to do is just try to maximize the frequency. We can also add a +1 to 4 instead. So let's see. Num operations is 1. Interesting. I was thinking of like using a similar approach to this problem here, where basically you can group the numbers by their modulus, by their remainder. I'm not sure if we can do the same thing here. You can achieve the maximum frequency of 2 by adding 0 here, okay. +5. Oh, right. But the thing is, okay. We can't do that because Here in this case, you're allowed to perform, but it's the same thing here. You can only perform it once. Let's see. Add an integer and arrange to the element. Wait, what? This returns the maximum number of distinct elements after performing the operations. Here we want the maximum possible frequency. So it's kind of like the opposite, right? If you think about it. Because here, we definitely want, like we actually want to minimize the frequency of elements in nums. But here we want to maximize it. And we can perform, but we only can perform it this number of times on nums. Whereas here, we can perform it once on every element, right? So in this case, the number of operations is actually equals to the length of nums. Interesting. Honestly, I'm not really sure how to solve this problem. But I guess we can try grouping them by the remainder first. We try derive a relationship from there. Yeah, I'm not entirely sure either, to be honest. Default date int for now in nums d of num mod k plus equals 1. Print d return 0. Yeah, this is what I was afraid of. So basically, if k is the number of moves that we can make, or the steps, right? In this case, one can definitely reach 4 if your k is unbounded, right? But in this case, your k is actually bounded because, wait, what about in this case? Isn't your k bounded here as well? Okay, you know what? I should ignore this problem. Maybe I'll revisit it later. But let's just focus on this problem, right? What about here? K is 5, but I can only do it once. K is 1 and you can do it twice. What's the constraints? 10 to the power of 5. Oof, that is hefty. Another approach we'll be thinking of, like using dynamic programming, but you probably have to keep track of the number of operations that you have left, and you also have to somehow keep track of the frequency of the elements in nums. So that could be a little bit tricky. Or maybe I can just think in terms of intervals. Can I? Can I think in terms of intervals? Okay, look, we can add an integer in this range. So we kind of can think in terms of intervals, right? Because it's not like we only add k. We can add any integer in the range. So we will bring our scatter draw. Scatter draw. So we have like 1 here on a number line. Yeah, maybe just do like 1. Hope that is huge. Do like 1, 2, 3, 4, and 5. We have like 1 here, 4 and 5, 4, and 5. And we can do it twice. That means we can extend this up to k times num operations of times num op. But that's the maximum extent, right? The maximum extent. This is like 0, this is -1, and we basically want to maximize. We want to maximize the number of dots, right, for a particular number. So if we draw a line here like this, Well, you can't reach any of it. Hmm. But if we draw a line here, I can do this, and I can do nothing here. Let's see the next example. Okay, that's not very helpful. Next example, can we guess the answer? Can we guess the answer? How do we guess the answer? Guessing the answer, what I mean by that is using binary search over the solution space. Not entirely sure if that is like 100% doable, but yeah. So let's say, what's the minimum frequency here in this input, right? The minimum frequency, let's call that min f. Well, the minimum frequency is always 1, and the maximum frequency is 3 in this case, right? Which is the length of the input. Minimum frequency is 1. So we can achieve 1, we can achieve 2, we can achieve 3. I think we need like a bigger example to derive to make some sort of observation. Okay, okay. Let's see. Let's say it's, I don't know, it's num sorted. I mean, probably doesn't make too much of a difference. We could just sort it. It's not that expensive. Let's say it's sorted, right? Let's say it's sorted. Nums.sort. There's 2 to let's say it's 9. Let's say it's 7, 9, 13, 17, 17, or something like that. Then we say k is, let's do k equals to 5 maybe, or some weird ass number like 7. Let's say we can perform it 5 times. Can perform it 5 times. Okay, maybe the input is a little bit too big. Let's say this is like 4 instead. This 3. Right? There's 1, 2, 2, 4, 5. Okay, short it out. Oh, that's not the one. This is the one. Check 1, 2, 2, 4, 5, 7, 9, 13. 9 and 13. K is equals to 4. K is equals to 4. Just put up. Up is equals to 3. Right, 3. Yeah. I'm just thinking like in terms of like two numbers, x and y. And it might be possible that x plus k is actually less than y. X plus k is less than y, but and of course y minus k is greater than x. But you can probably perform the operation twice and have them like made somewhere in the middle, and then whatever the number is z, you can increase its frequency by 2. That is one potential edge case you have to consider. Yeah, I'm not entirely sure what problem this is yet, but Like for example, if you have a number 3 and a number 7, right, and your k is equals to 2, and your operations is equals to 2, then in this case, you would actually just say, hey, cat k 3 plus 2 and 7 minus 2, and then you have achieve a frequency of 5, 5, right? I think that's a good case to consider. Oh, three, 7. Here, about here. 7. Answer here is 5. How is the answer here 5? The maximum possible frequency. So basically what this is doing is grouping all the numbers that can reach each other, right? So in this case, 1 can reach 5, 5 can reach 3, sorry, 5 can reach 9, 9 can reach 13. 2, well, they can reach each other, kind of, they're already belonging to the same, when they're already the same. Wait, how is the answer 5? Return the maximum possible frequency of any element in nums after performing an operation, selecting an index and adding a number in this range to it. Wait. 7 plus 4. 1, 2, 3, 4. That's 11. How is the answer 5? That is crazy. Wait, what? Oh, I see. Okay, that's because we don't have to add k. We can add integer in this range to k. Yeah, okay. Um, huh. Actually, what are the numbers of I is only up to 10 to the power of 5? Interesting, okay. Okay, let's draw it out then. I think we can try to draw it out. I think we actually might need a number line in this case. I don't think this is good enough. So here, we're gonna do like this. Then do like this. Yeah, that's good enough. 1, 2. Oh shit. Ah shit. 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's do one more. Okay, so 1 minus 4. This would be negative 4, negative 3. Actually, we just need negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. I'll just not talk. Okay, space is a little bit tight. Wow, I hope everybody can see what's going on. 1, 2, 2, 4. 1, 2, 2, 4. 5, 7, 9, 13. 5, 7, 9, and 13. We can do the operation only 3 times. How did they reach 5? They move these numbers. They move these numbers here. It has to be right. So 4 minus 2, 1 plus 1, 4 minus 3, and then they load up the frequency here. I actually think this might be an interval problem. This might be an interval problem. So you process the endpoints like this. So 1 minus 4, 1 minus 4. Why can't we perform the operations 3 times? Would be like this. This one would be like this. Is that an interval problem? I'm not sure. Oh, that's ugly. How I'm like imagining this is, okay, it's an interval problem, and we just count out the number of intersections, at a particular number, right? Is that good enough? But we have to use this somehow, right? Because you can imagine, if let's say we have uh like another 5 here, it actually wouldn't change the result in this case. But my algorithm will fail to pick up on that. 5. So the answer is still 5. So I was just thinking like doing a streamline algorithm, playing on the abusing the fact of the interval part. I think that is where the challenge come from. In the challenge of this problem, right? We can only do this number of operations. That means what? Do we drop this? Do we drop this as we go? Maybe. So we say, okay, we can extend the range of this particular element in this case. Oh, that's really ugly. Don't really have a good way of drawing it. So what I'm saying is, okay, we extend it like this. This means we're making an adjustment on this number, right? Then we say, okay, let's do another adjustment. We do another adjustment like this. That's two adjustments already, two adjustments. Um, what do we say here? This is the third adjustment. So maybe we say like, okay, this is what we're keeping track of. Like this. Oh, that's really ugly. Oh, all of them are ugly. So now there's like three intersections, right? Mm, but okay, then now we have to give one of them up. The thing is, which one do we give up? We give up this one. Does it make sense to give this one up? Which one do we give up? Hmm. It's not immediately obvious to me which one to give up. Hmm. Oh, the acceptance rate is so poor. Which one do we give up? Which one do we give up? I mean, according to the answer, we will choose one of these to give up. But what is the principle behind sort of giving this up? I see, I see. But it's a little bit hard to keep track of. So what I'm taking here of is the green lines basically it represents the number of operations that we have done, right? Wait a second. Represents the number of operations we've done. And it also means that these are the numbers that can be moved around, right? They can be moved around. So in this case, we can put this one here, or here, or here, or here, or here, or here, whatever, right? So in this case, we can push it up here, or push it up here, or push it up here. But we would give up this. We would give up this. Oh shit. mm, hmm. I mean, even if it's binary search, yeah, I could see binary search being like potential solution. So the minimum frequency is always one, and the maximum frequency is always the entire with the length of nubs, right? Thing is, we know the answer here is 5, which means what? Which means that technically we can achieve a frequency of 1, we can achieve a frequency of 2, we can even achieve a frequency of 3. Now by doing one operations, by doing one operation and doing two no op, right? Adding 0 to whatever number. Or we can but even if that is the case, even if we can binary search the answer, how do we verify it? The greedy check function. How do we do that? It has to be ON or better for it to work. We'll say, can we achieve a particular number of frequency by performing the operations? When we perform the operations, do we do it greedily? Do we do it or just it doesn't matter? Because like what if the answer is like cluster at the back and we just do the operations like that? Just do the operations like that. Without caring. Which one do we give up? They might be cooked. This question might be cooked. Holy shit. Fuck. Okay, let's forge ahead. Let's say let's say we ignore this. If try to solve an easier problem, right? Ignore the number of operations. Fuck that. Well, what do we do in this case? In this case, we just keep drawing lines, right? For so it's like this up to 8. Well, the line is always the same actually. Here it's just here. Yep. Seven. Reach to. Nope. Okay, I think I better draw it nicely. There's 0 to 8. This is 1. 1 to 9. 3, 3 to 11. 5, 5 to 13. This is 9 to 17. 9 to 17, give or take. So if we didn't have the operations, what would the answer be? We would just find the number of the maximum number of intersections, right? In this case, this seems to be correct. 1, 2, 3, 4, 5, 6. Yep, this would be correct actually. This would be correct. Well, but because we know that the number of operations is we can only move 3 numbers. We can only move 3 numbers. Let's see. It's interesting, numbers of I is always positive. Okay. So maybe we can iterate on each number. Okay, nice like that. Iterate on each number. You know, if at every point we can ask, starting from the minimum number, we can ask like, how many numbers can reach this number? How many numbers can reach this number? 3 numbers can reach this number by performing 3 operations. How many number can reach this number? So 3. How many number can reach this number? 3. Okay, now here is another thing. How many number can reach 1? 1 can reach 1. And so is 1, 2, 3, 4, 5 other numbers, right? But we say 1, 2, 3, 4, 5, 6, 6 minus whatever is here. That means at position 1, we can only move, the best that we can do is 1 plus 1, 2, 3, 4. Okay, but at this point, we want to say, okay, how many numbers can reach this number? Right, we have 1, 2, 3, 4, 5, 6. We have 6 numbers that can reach this number minus whatever number is already here, that's 4. So we do the min of operations. So the min of operations and whatever number is left. So min of 3 and 4. So we get 3, 3 plus whatever number is here, that's 5. Then we can check from here. Here means what? Here means 6 numbers can reach here. 6 numbers can reach here, and 1, 2, 3, 4, 5, 6. 6 numbers can reach here, but there are no numbers that are here. No numbers that are here. That means 6 minus 0, right? 6 minus 0 is 0. Sorry, 6 minus 0 is 6. Then we say 6 minus 3. Then we need to do the... okay, I think it's actually a straight line. But I just need to like flesh out my thoughts a little bit more. So at whatever number that we are at, we say, where's my text? But that's else. Now at num x, we ask how many numbers can reach x. This is provided by the number of intersections at the current sweep. There's a term for this. I'm not sure if like number of intersections uh, is the right term, but in either case, after that, we say can take like intersections minus counts of x, right? Okay, what is counts of x? Counts of x is whatever number that's already there without moving it. Intersection is the number of numbers that can actually reach the number x. This would give us the number of numbers. Okay, and then the number count. This is the number count that can actually reach x. Then we say, okay, the answer is equals to the max of the answer on but the min of the number count and number of operations, so num up plus counts of x. I think this might be it. So what this is trying to say is the number count is the number of, well, is the number of intersections minus whatever number is there without removing it. So this is the number of numbers that can reach x by moving it. So in this case, with 4. Then we want to maximize the answer, but then we say, okay, how many, it's a bit hard to explain, but basically we take how many numbers can reach number x, and the number of operations, number of numbers that we can actually move, take the min of it, right, plus whatever number that's already there without moving, right? Then we just want to maximize the answer in this case. Oh my god, I think this is actually it. Did I just like cooked my way out of this one? Okay, so what this means is we probably don't even need to sort it, but we do need a counter. So we say counts is equals to counter of nums, and then we say min num is equals to min of nums, max num is equals to max of nums. And we say for x in range of min num minus wait. For num in nums, this is the events. So we're doing a stripline algorithm. And then we can just do default date then in this case. Events for num in nums, so events append. Also, this is the start. Is equals to 0. Okay, what events do we want to process first? When is the end of the interval? End of the interval is actually n plus 1. I think we want to process the end events first. Yeah, okay, maybe not. Not entirely sure yet. Append num minus k. This is the start. Yeah. Then this is num plus k plus 1. This is the end. I want to process n first. Then we say so we actually have to keep track of each number. Okay, so we say events.sort. Then for I in range of length of events. Then we have the actually this is for x, I guess. Okay, how do we want to do the strip line? Say intersections equals to 0. Oh, actually, this is the frequency. How do I want to do this? Do we just iterate from min x to max x? Is that how we do it? Or can we actually jump? I don't think we can jump. Yep, we can't jump in this case. So we actually have to process from min x to max x. So that would be min x or min num, I don't know, min of nums minus k, max num, max of nums plus k. For x in range of min num to max num, increment by 1. What's the worst case here? The worst case here is, because our loop is definitely bounded by this for sure. So nums of I, minimum is 1 minus k to this plus this. So it's actually not that bad. It's like 3 times 10 to the power 5, right? Because you take 1 minus this, and you take the maximum number, which is this plus this. So you get 3 segments in that case. So it's only up to 3n. That is perfectly acceptable because it's still O(n). Okay. This is plus 1. Okay. But we need a pointer to events, right? We need a pointer to events. I is equal to 0. And you keep track of number of intersections, I guess. While events of I of 0. How do I want to do this? When do we lose a number? Oh, okay. When do we add a number? So when x is less than or equals, or events of I is less than, okay, less than or equal. Okay. Hello. Okay. Okay. Jesus. When events of I is less than or equals to x, we say I plus equals 1, intersection plus equals 1. But when do we lose it? I think you can just do this. If this is 1, if this is the start, we say intersections plus equals 1, else intersections minus equals 1, then the pointer, then we say the answer x equals to 1, I guess. Let's do 0, fine. So answer is equals to the max of answer of the min of intersections, and no, it's not this one. Let's see the formula. Intersections minus count of x. Okay. So say num counts is equals to intersection minus counts of x, right? Yep. So it's main of num count and the main of num operations plus counts of x. Okay. Let's see what's wrong. Answer is 2. Hmm. 0, 0, 1. There must be a bug somewhere. Is it this one? I hope not. I hope that's not the bug. Okay, fine. That's not the bug. Is this the bug? Nope. Okay, that means we have to go into deep debugging mode now. I feel like the logic is correct. X is a start. FCN. Let's see. Five 11/2020. That shouldn't be that bad. K is 5. So we have a 5 here. Wait, no. Oh, yeah. 5, 11, 20, and 20. Then we draw a line, green line, 5 to 10. Yep. This is 6 to 16. This is, oh, we need a few more lines. So actually in this case doesn't really matter, I hope. And yeah. So I expect intersections to be 2 at 6. 6, yes, we do. All the way until 10, and 11 should be 1. Okay, code seems fine. Code seems fine. 11, 11, 11 at 15 is actually 3. 15, yes, it's 3. Even 16 is 3, 17 is 2. What's num count? 17. Num count intersection minus counts of x. Yeah, yeah. How is it 1, man? Oh my god. Okay, let's see. 17. Let's see 16. 16. 16. Intersections is 3. Counts of x should be 0. Let's do this instead. Number of count. This is the number that can reach x. Yes, yes. At 20. Where's my counts of x? Oh my god. Okay. Okay. Uh, counts of x of num plus equals 1. Okay. Uh, print. Oh shit. I think this might be 8, boys. Is it fast enough? Hell yeah. Hell yeah, baby. Holy fuck. This was a tough nut to crack. Holy. See, I knew there was a binary search solution, okay? But, well, I don't know how to do it. Fine, so whatever. Let's see how they do it. Sliding window, huh? Well, take a look at this one and some sliding window solution. Let me see. Is there sliding one? Okay. Prefix sum. Interesting. Kotlin. Cool. Use a counter. Okay. Um, let's see the editorial solution first. Yeah. Let the minimum and maximum values be num times min, num times max. Next, consider enumerating the majority element of the target. Let the minimum and maximum values of nums be num times min. Assume for each mi, calculate the maximum number of elements that can be transformed into mi. Can then use f as a temporary result. To be honest, I don't really understand what this editorial is trying to say, man. It's too messy for me. Yeah, I saw nums as well. No, but I did. Topics. Array, binary search, sliding window, sorting, prefix sum. Interesting. I'm gonna read it later. I'm gonna take a break first before coming back to this. But anyway, yeah, we can show you my code. This is actually sweep line algorithm. Sweep line algorithm. The time complexity is actually it's actually like 3n, where n is like the range between the minimum and the maximum number, and this is actually for each number like 2 elements. So that would be like, oh, this is n log n for sure. So it's like, I don't know, n times, or 2n log n, I guess. I'm not exactly sure. Could be linear logarithmic time. I would venture to say it's more logarithmic time because of the sort. As your elements grow bigger, but this is definitely maybe this is the higher upper bound. Not entirely sure, but that's it for me. The space complexity is of course O(n) because we should use a counter, and the sort takes up O(n) space because of team sort. Python use team sort. But yeah, that's it for me. This is my algorithm. Thanks for watching and happy grinding.